Imagine this. You take two particles, you let them interact. Then you rip them apart, miles apart, planets apart, light years apart. Now you touch one, and somehow the other one seems to know. Not by text, not by Wi-Fi, not by cosmic pigeon. It responds with a correlation so weird, so precise, so deeply offensive to common sense, that Albert Einstein looked at it and basically said, "Absolutely not. This is nonsense." He called it spooky action at a distance. That phrase comes from the long argument surrounding the 1935 Einstein-Podolsky-Rosen challenge to quantum mechanics, which questioned whether the theory was complete. Later, Bell's theorem and experiments on entangled systems showed that the world does not behave the way local hidden variable intuitions would predict. And yet, decades of experiments kept coming back with the same infuriating answer. The universe is spooky. Not in the ghost under your bed sense, more in the reality is under no obligation to feel comfortable to primates sense. Experiments recognized by the 2022 Nobel Prize in Physics established Bell inequality violations with entangled photons. Modern treatments emphasize that these correlations do not enable faster-than-light communication. So dim the lights, open your mind, and put your classical intuitions in airplane mode, because tonight we are visiting the most unsettling relationship in the universe. For centuries, physics felt wonderfully reasonable. A thing was here or there. A cause produced an effect. An object had properties whether you looked at it or not. Reality, in other words, behaved like a respectable adult. Then quantum mechanics arrived like a raccoon with a flamethrower. At very small scales, particles stopped behaving like tiny billiard balls. Instead, they followed wave functions, probabilities, and measurement rules that do not match ordinary intuition. In the standard quantum formalism, systems can exist in superpositions. Composite systems can exhibit entanglement. The parts cannot always be reduced to independent states. Electrons were not simply here, they were described by a spread of possible outcomes. Photons were not just little bullets, they behaved like quantum objects whose properties become definite only in specific measurement contexts. And then physicists discovered something even stranger. Sometimes two quantum systems could be described together in a way that made no sense separately. That is the doorway to entanglement. A standard hallmark of entanglement is that the state of the pair cannot be factored into one state for particle A times one state for particle B. Imagine you create two particles in a shared quantum state. Not two separate particles with matching labels, not tiny twins pinky promising to stay in touch. No, one joint state. That means the full system has a well-defined quantum description, but the individual pieces do not carry complete standalone stories. This is the central conceptual point in technical explanations of entanglement. A simple example works like this. You prepare two particles so their spins are linked. When measured along the same axis, if one is up, the other must be down. Before measurement, quantum mechanics does not say each particle secretly carried a pre-written answer card. Instead, the pair itself is described by one shared state that produces correlated outcomes. Bell's theorem was designed precisely to test whether these correlations could be explained by local hidden variables. Experiments say no. So when people say entangled particles are connected, that can be misleading. They are not connected by a cable. They are not whispering across space. They are not running a secret quantum group chat. The correct idea is stranger and more beautiful. The two-particle system is one quantum object distributed across space. And yes, that sounds slightly illegal. Einstein was not impressed. In 1935, Einstein, Podolsky, and Rosen published the famous EPR paper. Their claim, quantum mechanics seemed incomplete, not because it made wrong predictions, but because it appeared to imply a world where measuring one system could tell you something about another distant system without a local cause. Einstein's instinct was simple. There must be something underneath this. Hidden variables, deeper instructions, a mechanism that restores locality. Which, honestly, is relatable, because if I told you two dice on opposite sides of the galaxy rolled in perfectly coordinated ways, you would not say, "Ah yes, spatially separated non-classical correlations." You would say, "Who rigged the dice?" Einstein thought the dice were rigged too, but then came John Bell. In 1964, physicist John Bell did something devastating. He turned a philosophical argument into mathematics. Bell derived inequalities that any local hidden variable theory must satisfy. Quantum mechanics predicted that entangled particles could violate those inequalities, which meant the question was no longer philosophical, it became experimental. Bell essentially said, enough arguing, let reality testify. If local realism is correct, correlations are limited. If quantum mechanics is right, those limits can be broken. Then the experiments began. Physicists including John Clauser, Elaine Aspect, Anton Zeilinger performed increasingly precise Bell tests. The result? Bell inequalities were violated, again and again and again, meaning the universe does not obey the combination of locality, classical hidden variables. Physics had to give up something, locality, classical realism, or the idea that reality behaves like classical intuition suggests.
Quantum mechanics did not just win the argument, it made reality confess on camera. Now we reach the part where the internet usually loses its mind. People hear measuring one particle instantly affects the other, and they say, boom, faster than light communication. No, entanglement produces correlation stronger than classical physics allows, but it does not allow faster than light messages. Why? Because the results of individual measurements are random. You cannot choose whether you measure up or down, you just get a random outcome. The strange pattern only appears after two observers compare their data, and that comparison requires ordinary classical communication, which is limited by the speed of light. So entanglement is not a faster-than-light telegraph. It's more like this. Two people open sealed envelopes in different cities. Each sees a random symbol. The symbols mean nothing individually, but when they later compare notes, they discovered the symbols were coordinated in a way no classical system could explain. Weird? Yes, but not a cosmic messaging service. So if someone tells you entanglement lets you text Mars instantly, please escort them politely to the nearest chalkboard. Entanglement attacks one of the deepest habits in human thinking, the idea that objects carry their own independent properties. Classically, that feels obvious. A coin is heads or tails even before you look. A glove in a box is left-handed or right-handed before you open it. Reality carries its facts around in its pockets. But entanglement says, not necessarily. For entangled systems, measurement statistics cannot be explained by assigning each subsystem its own predetermined values. Bell test experiments rule that explanation out. And this is where classical analogies break. Two gloves and two boxes are not entanglement. That is simply ignorance. Quantum entanglement is stronger. The correlations are not hidden classical keep-booking. They are fundamentally non-classical relationships. That is the wound entanglement opens in our intuition, and it does not close easily. Ironically, this philosophical nightmare became a technological tool. Entanglement is now a key resource in quantum information science. Applications include quantum computing. Entanglement allows quantum processors to manipulate correlations classical computers cannot efficiently represent. Quantum cryptography. Entangled particles can help build ultra-secure communication systems. Quantum networks. Experiments have already distributed entanglement across satellites and long-distance optical links. Quantum teleportation. Not teleporting matter like Star Trek, but transferring quantum information using entanglement plus classical communication. So the thing Einstein hated is now powering an entire field of advanced technology, which is a very science-like ending. A terrifying paradox becomes a startup industry. Entanglement tells us what predictions work, but it does not tell us which interpretation of reality is correct. Different interpretations of quantum mechanics exist. Multi-worlds, hidden variable models, relational quantum mechanics, information-based interpretations. They all reproduce the same experimental predictions. So if someone tells you, entanglement proves consciousness creates reality, be skeptical. If someone says, entanglement proves love is a cosmic force, be very skeptical. If someone says, entanglement means my ex still feels me spiritually, close the tab immediately. Entanglement is real, it is profound, it is experimentally verified, but it is not permission to replace physics with scented candles. The simplest, honest explanation is this. Entanglement means multiple quantum systems can share a joint state whose correlations cannot be explained by local pre-written values carried by each system separately. Or even shorter, the whole contains information the parts do not individually hold, which suggests something unsettling. At a deep level, reality may be less like a collection of independent objects and more like a network of relationships described by one shared quantum structure. Not magic, not telepathy, just reality being stranger than the species that evolved to throw spears expected. So what does quantum entanglement really mean? It means the universe is under no obligation to respect our classical intuitions. It means distance is not the whole story. It means correlation can be deeper than mechanism. It means reality is not built like a row of isolated lockers. And maybe the most humbling part is this. The strangest thing about entanglement is not that physicists discovered it. It's that the universe had the audacity to be this way. Einstein tried to save common sense. Bell forced nature an answer. And the experiment said, common sense is not the boss here. That's why quantum entanglement remains one of the most beautiful, brutal, mind-bending ideas humanity has ever uncovered. If you enjoyed this, type spooky in the comments. And if you want the next rabbit hole, we can explore Bell's theorem, quantum teleportation, why observation in quantum mechanics does not mean human eyeballs create reality.